And so this is a review of back in your freshman chemistry days when we talked about significant figures. And the significant figure convention is useful for reporting data, but it's also what you're left with when you have no measurement of uncertainty. So this is really one of your assumptions. If you're given a number, 4.2, you have to use the significant figure convention to estimate the uncertainty. And it can be dramatically wrong. Okay, but it's all you have sometimes. So if I tell you 4.2 inches, then you have to, and I don't tell you my uncertainty, you have to assume it's plus or minus 1 in a tenths place. So this is something like 4.2. You would assume it's plus or minus 0.1 inch is the uncertainty. And that's not a great situation to be in because it might be 0.5 inch uncertainty. And so we would really be too low on our uncertainty. We would think we were much more confident than we really are. And so this is deciding on what are significant figures. The significant figure for reporting is to report all the certain digits and one uncertain digit. And so they're telling us by this being the farthest right number from the decimal place that that's the uncertain digit. And so when we talk about digits being certain or significant, the leading zeros are not significant. So in this case, you only have two significant figures because the leading zeros are only telling you where the decimal place is. So is everybody cool with that one, right? You look at that and you say, yeah, those leading zeros just tell me where the decimal place is. And in order to check yourself, how would you write this in scientific notation? 1.2 times 10 negative 3. Okay? You would not write 0, 0, 1, 2. Right? That would be ridiculous. You wouldn't catch yourself doing this, and so you know those leading zeros are not significant. Because if you were to convert it to scientific notation, you would just write 1.2 times 10 to the negative 3. So if there is a decimal place in the numbers, then trailing zeros are significant. So 1.200, because there's a decimal place and we listed those zeros out, we didn't just cut them off, then we're telling somebody that those are significant numbers. And so again, it's about communication. If you write 1.200, you're telling me those zeros are significant by including them. So it's on the person who reports the data to do it correctly. It's your responsibility. Any captive zeros, meaning zeros between non-zero numbers, those are by definition significant. And then you should never, because you're misleading somebody, append, put zeros at the end that don't belong there. Okay. So if that last two zeros there don't belong there, then you've lied to me essentially. Right? You've told me, let's say this was a mass, and you have just one of those 3-beam scales that only measures to 0.1 gram, and you ended up writing 2 more zeros, then I think you spent a lot more money on your balance. Right? A lot of times it's about money. If you're reporting something with a really precise number, you're also telling somebody how much you invested in that measurement. Okay. And so then this is the tricky part, the multiplication and subtraction and addition rules. So for multiplication and division, you just maintain the least number of significant digits. Okay. So 11 times 0.05, 0.05 only has one significant figure. And so the result should be rounded to one significant figure. Okay. So I see some nods, that's good. The thing that confuses people is the subtraction and addition rules. Okay. It's not significant figures this time, it's decimal places. So place value is important for subtraction and addition. So subtraction and addition retain the least number of decimal places. So 11 minus 0.05 is just 11. Now that blows some people's minds, right? But why is that? You can understand why that is. Remember this assumption here. This will help you. When I look at 11, what's my assumption about the uncertainty? Plus or minus a whole dollar. And you're saying I subtracted a nickel? I'm uncertain whether I have 11. It might be 10. It might be 12. I can't keep track of nickels. Right? So I lost a nickel. That's fine. I don't even know I lost a nickel because I can't tell if I've got a dollar more or a dollar less. Do you see this? Why subtraction focuses on the place value? Place value is a more broad term than decimal place because there may not be any decimal places. There are no decimal places here, but there's a place value of ones. And so the most coarse place value, the one furthest to the left, is the one that restricts our addition and subtraction significant figures. And so this is still reporting all the certain digits, the tens, and one uncertain digit, the ones. I was uncertain in the ones here, and I'm still uncertain in the ones. Okay. Now, you could do the subtraction, so let's go ahead and waste some time. Okay. So I'm going to type 11, and I'm supposed to subtract 0.05. Why did I write 10? Okay. So I have 11, and I'm subtracting. I was uncertain, right? That was the thing. No, unintentional joke. I'm supposed to subtract 0.05. So I'm going to go ahead and write out the 0, and I'm going to say 10. Okay. So that's 5, and then 9. Okay. And then 10. So 10.95. And then this was the uncertain digit for that one, and so that tells me where to round. And so because that tells me where to round, this becomes 11. Okay. And so it's exactly what I was saying. If I'm uncertain in the ones place, then I really can't subtract anything that's below that. Okay. I'm not going to leave until we're good with that. Okay. Now, what if it's all in scientific notation? There's some practice problems for that. You want to get them all in the same place value. Okay. So if I have (1.1) times 10 minus 5 times 10 minus 2, it's the same problem, isn't it? Okay, so I'm looking at that, I'm like, ooh, I've got to get all of this, to the same place value. So I would just get them out of scientific notation. And so this right here goes to 11. That goes to 11. And that's 0.05. Okay. But this is my uncertain digit there. That's my uncertain digit there. So this tells me where to round. So it's the same problem we had before. Just get out of scientific notation and do the subtraction. Pretty cool. Look at that. Okay, so that's the significant figure convention. Now we still use this sort of this rounding idea, the multiplication and subtraction rules with when we do know this uncertainty. Like if we knew it was plus or minus 2 in this, it really wouldn't change. We would still round to that ones place. But we're going to now learn about standard deviation and how to calculate that uncertainty. Right now, with significant figures, we're just assuming it's plus or minus 1 in the end, in that last digit. So let's learn about some statistical terms. And so a sample would be a small number of measurements, so n equals less than 15. And for the mean, we're going to use x bar or x in these angle brackets. So there's a couple of different ways to write the mean. And the population is an infinite number of observations, so greater than 14. Did you know that 15 was infinity? So now you know. We'll see why this really is, there's not a hard and fast cutoff, but we'll see in a second. I've plotted both, and you can see that they do approach each other when the samples get up well above 10. And so for the mean for population, we use the Greek character mu. Don't confuse it with micro, the prefix for the metric system. So mu written by itself is the mean, but for micro, it's a prefix. And so it would be micrometers or micrograms. It would be mu g or mu m if it was being used as a prefix. So context is important. If you see mu by itself, we're talking about the mean. And we're saying that we've collected a lot of data to get the privilege of using mu. Right? If you only had 5 samples, then you use just X bar. And then we have the standard deviation. Let's look at the formulas for standard deviation. And many times I find that students have never taken this formula apart. So if you look at the different parts, and let's think about the word. What do you mean? And today's question is, what do you mean by that? Okay, so I say the word standard deviation, and you think in your mind, what do you mean by that? Well, let's take it apart. What does deviation mean? It's fluctuating, right? And it typically deviates from something. And so this is deviation from the mean. Where do you see that in our formulas here? Where do you see deviation from the mean? Right. That's what this is right here. That's deviation from the mean. And same down here. What's standard about it? It's a manipulation. We've squared them. Why would we square the deviations? Yeah, to make them all positive. That's always a nice mathematical trick. If you want to know how much your data deviates from the mean, and you're trying to sort of average those deviations, you're going to have the positives cancel with the negatives. And so let's square each of them so that when we sum them together, the number gets bigger. If we have lots of deviations, then we'll have a huge sum of those deviations. But that'll be too big of a number, and so we want to divide it by the number of data points. So we're taking the average, aren't we? You sum something and divide by the number of measurements, that's the average. So another way to say this might be the average deviation. So that word standard is another way to say the average deviation. Yeah. And then we take the square root. Why? Well, because we squared them before. That made them too big, and now we're going to take the square root to get them back down on the level of the original measurements. So now it's not just a formula. You can read it like a paragraph. You look at it and say, okay, here's my deviations, and I'm squaring them to make them positive, dividing by the number of measurements I have, and then taking the square root to get back down on the scale of my ruler, whatever I was using to measure with. So those are the standard deviations. Now, the sample has n-1 in the denominator, and the population has just n. And so why is that? Remember what are we reporting the standard deviation for? Say again? Okay, yeah, for our control chart, we're deciding whether we should take action. Is it better to take action a little bit more often to keep things tighter, or to just stand back and let things get as bad as they possibly can before we take action? We kind of want to present the bigger number, don't we? We want to present a more conservative estimate of our standard deviation. We want it to be a little bit bigger. If given a choice between a slightly bigger standard deviation and a smaller one, we probably want to report the bigger one, because we're telling people the worst case scenario, right? And so we're dividing by a smaller number here, which makes our answer bigger. And so we're giving for the sample, we're giving a slightly bigger number. Let's look at the chart. See, the red is the standard deviation with the n-1, and the green is the standard deviation population. And for small numbers of measurements, the green is really too small. It's too confident. The red is more conservative. We're giving people the worst case scenario. Okay. There's a statistical reason in terms of calculating the mean. You reduce one of the degrees of freedom in the data set, and so it's a little bit more accurate to use the n-1. But notice how you get up around 15, they're essentially the same. It's really not much difference between the two formulas. But there's a substantial difference down here. If you measure 3, like in lab where you did 3 titrations and you calculated the mean and the standard deviation, you definitely want to divide by n-1. You want to divide by 2 because you did 3 titrations. And that gives you a larger uncertainty. And so again, it's about communication. You're communicating the larger uncertainty, not the smaller one, to someone. Now, if you had several measurements, let's say this group did a measurement and standard deviation, and that group did a measurement and standard deviation, how would we pool those standard deviations together to get it for the whole group of students or analysts? Because y'all might have a different mean than you. And that's called the pooled standard deviation. So we're pooling everybody's data. So we're taking the standard deviation from this group and combining it with the standard deviation of that group. Now you might just say we average them, right? We add yours to theirs and divide by 2. But that doesn't really work because there's 4 people in this row and 3 people in that row. And so you've measured it 4 times and have a better picture for your standard deviation. And you measured it only 3 times and have a less of a picture for your standard deviation. And so the pooled standard deviation is just a weighted average. Notice here, here's the standard deviation pool. We square it, and then we multiply by n minus 1. So you have 4 people, so we multiply by 3. And here we square yours and multiply by 2. And so you got a 3 to 2 ratio. Yours is weighted 3 and yours is weighted 2. And so your results, because there's 4 people in your group, are given more weight because it's a better determined number. And then we divide by all of those numbers, and so minus however many groups there are. And so it'd be your 4 plus 3 minus 2, and so sort of the weighted average is what it is. And then we take the square root to reduce the squares. So it's pooled standard deviation is pretty easy, but you got to know how many measurements were done in each group. Now, uncertainty in measurement. I've talked about keep all the certain digits and one uncertain digit. It's still out there. We still have analog meters, and so when you're reading something on an analog scale or volumetric glassware like a burette, you have those little tick marks. Right? You should be able to estimate half a tick mark. And so we're looking over here on the left, we see 125 and 126. We're confident it's at least 125, and we're confident that it's less than 126, and so we have to estimate what it would be. And you can estimate to 0.5. You're not really asked to estimate to 0.3 or 0.4 or 0.7, but if it's between those numbers, you could say it's probably 0.5. Okay? And so you would write that down as 125.5. Now, which numbers are you certain about? The first 3, 1, 2, 5, because you know it's bigger than 1, 2, 5, but you're uncertain about the 4th. And so that's your 3 certain digits, 125.5, that's your uncertain digit. So you record all 3 certain digits and 1 uncertain digit. The same thing on the balance. You're looking at that, you see the number, it just won't settle down. You sit there and wait all day long, it's never going to quit. Okay, and so you're saying, what am I doing here? So you're definitely uncertain in that digit. It won't stop changing. And so 125.5, or you might write 0.4, or if it's equal time, sometimes just because of the calculations and I want to, keep a guard digit, I'll write 125.45, but I'm keeping 2 digits of uncertainty there. Okay, and so that can be done. But it's acceptable at a minimum to estimate 1 digit beyond the tick marks in an analytical readout. Now it can evaluate our measurement system, and so the instrument literature will give you an estimate, like the balance may say can measure to plus or minus 0.2 grams. So if you put a weight on there, daily or over time, it'll measure the actual mass to within 0.2 grams or 0.2 pounds on the previous thing. And so we make these calibration weights that you should never touch with your skin because your oils and all the acids in your oils will react with the metal. But anyway, you can buy these little weight sets and bring your balances into control. So verification and control charting should be done, and you should work against a primary standard. what's interesting is that these standards cascade. So mass is typically the foundation. So we will use a standard weight to standardize our balance. And then with that balance, we can standardize our pipettes. So it says it's going to put out, let's say, 0.1 milliliters. And you know the temperature, that's close to room temperature, so the density of that liquid should be 1. Okay, so it should be 0.1 grams. And so you can sit there and put in 0.1 mils, and so you get a little weigh boat and your pipette and DI water, and you measure the temperature, and you can look up the density, so you know how much mass you're putting on the scale. And you can be really wasteful and dumb about this and put a 0.1 on there and then take that off and throw it away and put another weigh boat on, tear it, put another drop on there. But that's really wasteful. What you really want to do is just have the weigh boat there, tear it out, get your pipette, measure the temperature, write down the density from the CRC, and put 0.1, and then 0.1, and 0.1, and 0.1, and keep adding 0.1. And so it's going to get heavier. It's going to go, the mass is going to read 0.1, 0.2, 0.3, 0.4, 0.5. And you get into Excel and you write down all the specific measurements, and that slope should be 0.1. Okay? And you get the ANOVA output, you do a linear regression, and you get the uncertainty in that slope value, and it'll tell you the uncertainty in your pipette. So it'll be 0.1 plus or minus whatever the variability was in that slope. So that's a way to calibrate your pipettes. So calibrated balances produce calibrated volumetrics, calibrated pipettes. And then those calibrated volumetrics will calibrate your instruments. And so you do all your standards, you run them on a control, on a calibration curve, and then you can see how well your instrument performs. But if your balance is crummy, then you may think it's your instrument. If your technique is crummy, you may think it's your instrument. The instrument may be working great, but you don't know how to pipette because you keep pushing it out, all the way. You do 2 pumps, you know that's not right. And so then the calibrated instruments validate methods and these round robins and so on. They come around, you're supposed to run this method on this sample, and your lab is over here and everybody else is over here. And no matter what they do, they can't get you to come in line with them. They may send somebody out to your lab and validate your method. So they sit there and watch you do the things that you do. And that's a really high stress. Okay? Someone's watching you pipette and they see you do it the wrong way. And they're like, we found it. Instead of being in trouble, you'll probably just get retrained. They'll say, okay, we need to make sure they will be excited to have found the issue. Okay? But you might get a talking to. So they might say, look, you shouldn't have done it that way. Because they will have gone through a lot of scrutiny up to that point. But each step affects the overall uncertainty. And so this propagation of uncertainty is a critical skill that we'll talk about. So we did some of this in the fall. We'll revisit it just so that you, again, get very good at it. So this numerical result without an estimate of its uncertainty is useless. It makes the person that you report to have to make assumptions that may not be founded. They may assume it's plus or minus 1 on the last digit, and it's not. It's higher than that. So directly measured values can easily be estimated, but multiple measurements require standard deviations and so on. So we will use these formulas. Let's go back again. Remember, sigma is that population uncertainty. So wherever you see sigma here, think of standard deviation. So this is the standard deviation in C over the value of C. And if I were to rewrite these formulas with populations, I would just change all the sigmas to S's. Pretty straightforward. Okay. So wherever you see a sigma or an S, that's your uncertainty. Now these formulas can be simplified a little bit. I've simplified this one. Notice that if I square both sides, I get rid of the square root and it goes over onto the left. So the uncertainty squared in the result y is equal to the sum of the uncertainty squared of all the pieces that I put together. So this is a really simple way to write out the one for y. It's just the sum of the squares of the uncertainties of everything that was added and subtracted. So if I'm doing a calculation that has addition and subtraction over here, then this is the formula that I use to calculate the uncertainty and the result being y over here. And I can understand there's an uncertainty in y if I know the uncertainties of a, b, and c. Now, if there's a number in there that I don't know, like a or b, and I don't know the uncertainty in those, I'm going to have to use that significant figure convention and assume it's plus or minus 1 in the last digit. Okay. But a lot of times I can look those up. Let's say we're calculating a molar mass. I'm not going to use the periodic table, although manganese is pretty good, 54.93805. Okay. But there's no uncertainty listed there. So what do I have to assume? I have to assume it's plus or minus 1 in that last digit. But that's down in the 5th decimal place. And that's okay. You know, that uncertainty in the 5th decimal place is not going to impact my data probably because my balance doesn't measure out to 5 decimal places. Okay, so products, multiplication and division. So here's my y value for that. And if I know the uncertainties in A and B and C, I can calculate it this way. Notice those are relative standard deviations. These right here are RSDs. So that's the standard deviation of C over C. So that's the RSD for C. And then you square that and add up to the squares of all the other RSDs. And notice here, if I wanted to get y back over on the left, I would divide both sides by y, and so I would end up with y over here. And if I wanted to get rid of the square root, I would square this. And I would end up with this equation over here on the right. So for multiplication and division, it's just the sums of the squares of the RSDs. And for addition and subtraction, it's just the sums of the squares of the standard deviations. Exponents is just a special case of the multiplication because it's a number multiplied many times. So in this case, it's a number multiplied x times. And so it's just the x times the relative standard deviation. Then we have log examples and anti-log examples down below. So what we're going to do is we're going to put this into action and actually measure things. So let's see. So I would like for, let's go with U4 here plus U. So U5, this is your set. So measure the circle. Okay. And then back here, U5. Okay? So pass out the ruler and a circle to everybody in your group. Okay, U5 right here. There we go. There's your circles and rulers. And then let's go with you in this. Oops. One go the other way. Let's see each other. So you with your game. Okay. And then you with this. Okay. So measure the circle. Okay. And talk in your group. Don't talk between groups. Just talk within your group. I know. I'm assuming it looks like the big chicken.
I circled off the top.
Yeah, that's
That's all you can
Yeah, those who have a little more on their paper, and you have a little better answer there.
Yeah, in the middle of it.
Right. That's all I had to remove the outside. That's all I got to work with.
So if with your group, calculate the average and the standard deviation. So I'm going to get those up here.
But both of the last ones would be inserted. It measures the point range.
I think all the things are yours. Yeah.
Oh, are you serious?
Based on our answers, y'all have to use it.
Wow. You're right. What's 1 12 to the air? Or a couple of them. 1 divided by 4. So that's 4 easier.
Yes. If I had to do natural abundance, then those are averages, the natural abundances. So that's my moderate guess. I don't exactly know why. There's some different, like maybe. I would assume that maybe it has a little more standard.
0, 8, 2.
Yeah.
0, 8, 3.
It also may be.
I have no idea how to report this.
I don't know how they're average. You've had a 10. Do y'all have an average standard deviation? You do?
I was ready to hand you this Okay, well,
There you go.
just capture. Okay, well, apparently I need to put batteries back up
I wouldn't use inches at all. Fair point. But y'all need to be consistent with your metrics, right? The other side, yes. Do y'all have the mean communication? What?
I was like, you can't just put it in there.
Yeah, if you have that.
Make sure. Everyone's right.
3.5, 3.4,
There's a lot more than that for air.
Yeah. Okay.
Well, also, yeah.
It's like in thirds, right? 0.3, 0.7. Yeah. You may. Okay, so group 1 is average.
Our average is
2.2?
10.2.
10.2. And the standard deviation?
Working on it.
Okay. Anybody else ready with an average?
That's centimeters.
Centimeters, okay. Don't even change your procedure based on what you hear. Okay, so we'll do units together. Y'all are isolated groups. Yeah, so you can't communicate with each other. Did you have a standard deviation? Okay. What did y'all have? Okay.
It's all uncertain regardless.
Okay, what about that?
3/4.
How long you get?
Oh, see, that's the.
Okay, so do you have a standard deviation? No, okay.
So, first you put it into your y.
Y'all are slow on the standard deviation. Yes. 0? Okay.
0.
Which group were you? 3?
The 3, yeah.
3, 1/12. Yeah.
Yeah, that's
Okay.
Right?
Yeah.
Okay, here we go.
What's your average? My method is on the
Yes.
It was 3.2.
That's your standard deviation. Okay, group 2. Okay. That's some symbols.
Always.
I find the standard deviation calculations to be most easily done in table format, where I have my 5 measurements, and then I have the mean down at the bottom, and then I take the difference between each one, make a column, and then sum that, or square it, and then sum it.
That's without having any error, yes. So,
Point oh four? Okay. On group 1, yeah.
and it also gives us our mean and
Yes. Do it that way.
everything.
Yes.
0.05.
Yeah.
0.05. Okay. All right, so let me ask you, what comments can we make on our reported data? The circles are all the same. Okay. Yeah, units, that was the thing. Some people, but you did report, you said. So who said? You said centimeters, right?
No, he said centimeters.
Who said? You did? Group 5? Centimeters, yeah. I just didn't want to write that down because I didn't want to get the other group to think about what units. So y'all did report them. You reported them. What about y'all? Did
Centimeters.
centimeters? 5.21? Yeah, centimeters. And y'all did inches?
Yeah.
Okay. Okay. So that explains some things, right? And then the 3/4. Yeah, there are no units on your ruler.
I think there's no units on ours either. It sounds like
We assumed it was a
Yeah. And so y'all's was assumed. So that's a comment, right? 3
Oh, we
was assumed, right?
Okay, that explains these measures.
Another
What's
comment
going on?
is we included the border around.
I'm glad we got
Okay, including
stressed out.
thick line or border.
Comment on our stuff. Yeah.
Like did y'all, that's something did everybody include the border? Did you measure to the outside of the border or to the inside of the border?
To the best of our ability, some of our circles are cut off.
The outside.
Yeah.
To the outside?
No, our outside's cut off. Yeah, see, our outside's cut off. Some of our.
Not all the way around though.
No. Well,
Did you choose to use the place where it was cut off?
See, we should. Yeah.
One of them was a bit on the three side.
You couldn't find one trace across that would get. Yeah. So the point is, yeah. Okay, what other comments looking at the data? So let me bring everybody back. What other comments do you see? So there's an issue with the units, right? There's an issue with the units. What if I send your reports back, group 3 and 4, and I send your reports back and I say you need to report in decimal places? Okay. Okay, so this one's 0.75, so we'll convert this back to 0.75. You guys give me yours.
3.08.
3 point what?
08.
0.8.
Well, and then repeating 3 as well.
And the 3
So those
repeating.
last two digits are
Okay. Okay. And so now what comments do we have?
Yeah.
Definitely we can see. Yes, our instruments are all different. Okay. If I look at this and I say these are all high, even if I was familiar with every instrument, I said these are all high by a factor of 2. Y'all are awful. How can you reconcile what I was expecting versus what you measured? Yes. What if I was asking for the radius? I didn't say it. I just said measure the circle. Measure the circle is a crummy instruction. And so your immediate question should be, what do you mean by that, right? What do you mean by measure, right? Yeah. And I'm not faulting you. I'm trying to emphasize the point. Always ask for definitions of terms. It's called an operational definition. I'm about to operate, and I need a definition. I need to know what the operational definition for measure is in this case. Okay? What other questions should you ask? What unit do you want me to use? I've got this crazy thing in fractions of unit. What is that? Yeah, the one over there just has fractions all the way up, and the biggest number is 1. 0 and 1, and a bunch of fractions in between. And so it's really strange. It's like 1 inch expanded out. Okay, centimeters versus inches. Now, I mean, if they're both accurate, then we can convert one to the other. But, that's okay. But we created a problem then when we went from fractional measurements to decimal places. Because now when I see the decimal place, what is glaring at me? What's glaring at you? We've all of a sudden increased the precision of our instrument. This one has infinite precision. Because it goes out to the repeating 3s, forever. And so this raises an issue, especially, well, maybe it does go to infinity because we have 0 standard deviation. We know it is exactly 3 and a 12. And this was exactly 3/4. And so there's infinite precision for that, but it's probably not infinite precision. So we need to figure out a way to estimate that uncertainty. Okay. So our means are all over the place. But let's look at this for a second, taking those middle 2 out. Even if, let's say we converted this to inches, and who knows what we're going to do with this one. But we could still calculate a pooled standard deviation. Right? So what's the standard deviation for the whole class? Right? Let's calculate that. So S pooled is equal to the square root, and it's going to be the standard deviations for all the groups squared. So 0.04 squared times 5 minus 1 plus 0.21 squared times 5 minus 1. Don't enter anything in your calculator just yet. Plus 0 times 5 minus 1 plus another 0 times 5 minus 1 plus 0.05 squared. My zeros are squared, by the way. Times 5 minus 1. And then that's divided by 5 minus 1 plus 5 minus 1 plus 5 minus 1 plus 5 minus 1 plus 5 minus 1. Okay. So that's all of the different degrees of freedom for each of the groups. If there was any group with 4, then one of those would be a 4 minus 1. Okay. And so you can see that I'm going to have, if I could simplify this, I have 5 of these 5 minus 1s, don't I? Okay, so I'm going to mark a line through that, and I'm going to say 5 times 5 minus 1. And then I'm looking at this fraction, and I've got a 5 minus 1 on each of my terms at the top, and a 5 minus 1 on the bottom. And so I'm just going to cancel that out. Since all groups are equally rated, then it's just the average of all the standard deviations. Right? I've got 5 standard deviations and I'm dividing by 5. That's really cool when everything's equally weighted, have the same number of people in each group, then it's just the average of all the standard deviations. So now we can use a calculator. What's 0.04 squared? Like, oh, oh, 0.06. Is it 2 O's or 1?
2 0.
0.16, okay. 0.21 squared.
0.0441.
And then 0.05 squared.
0.0025.
So add those 3 numbers together. Divide by 5. And take the square root. It's not that bad. So don't be, the pooled standard deviations shouldn't be a mystery. Turn my camera here. So that's the calculation. Yeah, we can see that. Does anybody have a result for me?
Of 0.00964.
964. Okay. Now, the question is, where do we round this? Remember what this number is. This is the measurement of the uncertainty. And the convention is to keep 1 or 2 digits of uncertainty, never 3. And so you can round it at the 9, and you can round it at the 9.6. Okay? But to keep all 3 is not useful. Okay? And so I would say this, make it 0.0096. Okay? Now this should have a unit, but we've got a problem with our system. Well, now we're talking about, it ends up being centimeters. But, standard deviation has a unit the same as the mean. Okay, so it'll be centimeters. One thing that I would like to point out here, though, is some mismatches. So this one here, we've got a problem. And this one also has a problem. So I would count off for both of those. If I were grading this assignment and we're looking at the results and how they were reported, I would count off for this. Why is that?
Because it needs 10.2 is a measurement that's on the ruler. You need one extra number of uncertainty.
Yeah, and so if you've got this, you're saying you're uncertain in the hundredths place. And here we don't have it reported to the hundredths place. And so these numbers have to match. We should keep all the certain digits plus 1 digit of uncertainty. And so the standard deviation tells you where to round. Okay. And so this should be corrected if it's, if it came out to be 10.20 and a bunch of zeros, and you did the standard deviation calculation and it showed you that you were actually uncertain in the hundredths place, then go ahead and put a 0 there. Okay, so that they match. So the reported number and the standard deviation should match in place value.
I was just going to say the camera wasn't.
Okay, thank you very much. So this is what I'm talking about, this mismatch here of the reported values and the standard deviation. So the place values should match in those. Okay. We can see that reporting in fractions is problematic because if it's plus or minus in the last digit, what's the last digit? It would be plus or minus in the 3 here. That's a real problem. And so we really don't know how to report uncertainty in fractional numbers. And so convert everything to decimal places. But then we have to decide where do we round the decimal place. This one goes to an infinite number of decimal places. And so that's a real problem. And it is a real problem because we didn't have any different results. We got 1 and a 12. or 3 in the 12th from all 5 people. So, this is a real tricky situation. Okay, could you say it was plus or minus 1/12, or maybe half of a 12? So plus or minus 1/24. Like if that's where the tick marks are, then that's your uncertainty, and so then you can convert that over to where your uncertainty is in the decimal place. So we've covered a lot of little tricky details. What things have popped up in your mind that you want clarification on? Let's summarize. What is the number one point that you gained from this exercise? Ask. Thank you. I was hoping someone would say ask, right? But ask specifically what? Jared, what do you think? What would you specifically ask? I said measure the circle.
Oh, well, yeah.
What do you mean by that? Yeah, exactly. What do you mean by measure? Yeah. Now, what's a follow-on question? You've got a ruler. Give me the units. Yeah, tell me centimeters, inches. Ask more about the instrument. What the heck is this? And I told y'all I wasn't going to tell you. You had to define it yourselves, mainly because I wanted the ambiguity. But I would, you guys would say, well, then we're not participating. Right? I don't know how to use this instrument, so don't make me report anything with it until you train me on it. And so it's like giving you the keys to the ICP-MS if you've never used one. Here, go measure this water sample. What do you mean? Is it wet? What do you want me to measure? Metals? Organics? I don't know anything about this ruler called an ICP-MS. And I don't even know what it measures. Is it, organic contamination? Is it metals? Of course, it's metals. You learn that in instrumental. But if you didn't know that, let me get y'all's ruler. I'll show them what it looks like. Yeah, pass them around. This is their ruler. This is their unknown instrument. Yeah, y'all got it nice. That's the best one. Yeah, so measure the circle with that. Yeah. And y'all's was too short, right? How did you think?
Yeah, it doesn't even go across the circle.
It doesn't even go across the circle. And so how? I mean, I'm almost calling. You couldn't even get the thing to go across the circle, so everybody got the same answer? That smells. Maybe this is I should just draw the poop emoji. Eyeballs on there. And because you had to actually move the ruler, and y'all did it exactly the same way. Yeah.
So the more precise an instrument gets, the more a bigger standard deviation it has?
Not necessarily. It just gives you more decimal places here, typically. So it's measuring I guess I should ask, what do you mean by precise, right? Really precise means it gives a very similar answer over and over again. Maybe not the exact same answer, but very similar. Okay. And that's why we like this relative standard deviation term. So you have your uncertainty, and that's your noise, right? And this kind of noise over signal. So you've heard of signal to noise, but noise over signal is the relative standard deviation. Your uncertainty over the value you measured. And so let's calculate those for a couple of these. So here we have 0.04 divided by 10.02. So RSD maybe a different part. Is equal to the uncertainty on top, 0.04, divided by 10.20. I'm going to go ahead and do that. And so would you please, someone do that for me? This is actually very good. Okay, I don't need a calculator to know that's 4 parts in 1,000.
0.0039.
0039. In other words, 4 out of 1,000. And so you can just look at the fraction and say, wow, my uncertainty in group 1 is 4 thousandths. Everybody see what I'm doing with the decimal places? I'm just moving everything over to the same place value. Let's do it for this one. No, let's do it for this one. So RSD here, we're almost out of time, I realize. So 0.21 over 5.21. See, I can look at that and say 2 parts out of 50 or 1 part out of 25.
0.04.
Yeah, 0.04. So your relative standard deviations give you an idea of precision, and so I could an instrument that's precise, I would say has a good relative standard deviation because it gives you a good, strong answer with very little uncertainty on top. Okay? If you flip these, you kind of have an idea of signal to noise. And so what's the inverse of this one? It's 2.5, right? 5 over, no, let's do it again. I can't do math in my head. Okay, so 1 over RSD. About 20, 22. What is it?
Yeah.
25, okay. And then let's do 1 over this one. Quickly, because we're out of time. It would be 250. 250. Okay. So you see how this one has a higher signal to noise, if you will. It's 250 versus 25. So that's a lot about data manipulation. We'll do propagation of uncertainty in details next time. And so work on your report today and get that thing in by tonight. And if you've already submitted it, don't worry. I have it to where you can submit multiple times. And so I'll just grade the best ones. All right? So don't worry about getting it reset. You can take the rulers and the circles with you if you want. It's your souvenir from today. That's fine. You can give them back to him. It doesn't matter.
Right.